He'll introduce the general topic that they're talking to us about today, and Alessandro then will get into details. Thank you, Luca. Thank you, Alessandro, for being here, and thank you everybody for joining us at this
okay with you?
early time.
I take off the mask.
Yeah,
You
yeah.
can hear me better. Okay, first of all, I would like to thank Stefano for the nice introduction and for the invitation. So we took the chance while in our way to San Diego for the optical fiber conference that you might know is I think the biggest conference worldwide for optical networks, to pass by and to visit Stefano here in this nice location. I always like Boston. Actually, Boston was the location of my first conference in 1998 at the Heinz Convention Center. It was Photonics East.
Yeah.
And I always like to visit Boston. So thank you very much, Stefano, for hosting us. And yes, as Stefano said, I started in 1995, 1996 working on optical networks when I was doing my thesis for the laureate degree at the Polytechnic of Torino. So let's say it could be considered equivalent to a master's degree, even though when we moved to Texas, they said,
Maybe
not exactly. But then they got to learn that we were well prepared. So the next people that came were already accepted as a master's student, so they could go to the PhD right away. And so my interest moved, but I'm always, let's say, more focused on the fixed part of the network than on the mobile part. So more on the, even for 5G or next generation mobile communication, I'm looking more at the wired part, so not on the radio access technology. But as you know, and the title of the talk says everything, now communications and computing are kind of a single entity in the network. So this is actually the trend. So that's why I entitled the talk When Communications Meet Computing. Actually, I think I took this title from a song that I think is a Christmas song. So when the river meets the sea, is from the Muppet Show, or the same motto of Muppet Show. So a brief outline of the talk. So I try to stay in 35, 40 minutes if I can. So I will tell you who we are, where we are located. I will take a look at into 6G or next generation mobile communication. Then, as Stefano said, I will tell you a little bit of what we do in about zero-touch networking, and then I will focus on one interesting, and I think is a new topic that we are exploring. And by exploring, I mean that we are at the beginning for confidentiality preserving analytics for failure detection that can be applied to optical networks, but to networks in general. And then in the name of the interdisciplinarity, we are also working on telemedicine. So application of, well, actually in this project, we have the task of looking at the connectivity part and how connectivity can help telemedicine. And then I will draw the conclusion. So, who we are? We are Scuola Superiore Sant'Anna of Advanced Studies. In short, in the project we are addressed as SSSA. We are located in Pisa, where the famous Leaning Tower is. Sometimes it's misused in the pizza boxes. And I still remember. And but so we are very close to the sea. The weather is enjoyable. I must say that there is not only the Leaning Tower and the Miracle Square in Pisa, there is much more, but unfortunately tourists don't know. Or fortunately, yeah, but and so and this is where this place is where the headquarters of the Scuola Superiore Sant'Anna are. This is in the city center because Scuola Superiore Sant'Anna was born as a college for, well, actually it was a college and a residence for nuns. Then it was transformed into a medical college. And then only in 1987 received the status of public university. So we are quite young. Then how do we do with numbers? Well, let me make this disclaimer. I'm not looking too much at numbers, but this is how now we are classified. We do quite well. I mean, you can see an interesting point is that the number of students and professor is really good. So is one professor out of 7 students. So it's a very small environment in which really students are in a college. The Scuola Superiore Sant'Anna
question. The Scuola Superiore Sant'Anna is only a graduate school, or do you have undergrad?
You know, we don't have undergrad. The undergraduate students, so we have undergraduate students that are resident in the college.
Yes.
Usually for engineering is about 15 students that are enrolled per year.
Oh, wow.
Out of this year was out of 350 applications.
Okay. So it's like normal.
It's exactly like normale. So normale is for philosophy, for mathematics, physics,
yeah.
And while Sant'Anna is for applied science. Yeah. Exactly, it's exactly normale. So we have these complementary courses that are for the student to stay in the college. Yes. So they must have an average score of 27 out of 30 throughout the studies, but they must be enrolled in University of Pisa. So this is how it works for undergrad. We can have master programs together with other universities in Italy. We cannot have our own master courses right now, but we do have our PhD courses. So we run PhD courses independently of any other university. So we basically are in the D World University ranking at the first at the national level on a census of 17 institutions. Why 17? Because we are classified in the small university. So we compare ourselves with the small university. So we cannot compete, obviously, with the big universities. So now Polytechnic of Torino, Milano.
What do you mean by small?
Small, I don't remember. It's just, I think, is in the size of it depends on the size of the professors that are there. But I think it's around 200. I mean, very close to our numbers. And we are 14th at the international level on a census of 790 institutions and 7th at the European level. If you like to look at the citations, we got about 60,000 citations and a field-weighted citation index of 1.62. But these numbers change a lot.
We are convinced. Send us your students.
Yeah. Then, what do? We have, you see, applied science. So it's biorobotics. Dear Polis is, let's say, political science and law, economics, management. This is our institute, so the institute where I am. So it's telecommunication, IT, and photonics. The Institute of Mechanical Intelligence, the Center of Plant Sciences, and the Crop Science Research Center. 2 departments of excellence. These are the old ones because the Italian government granted this long-term grant to the Department of Excellence. So we have 2. One is on the social sciences, and the sciences, and the one is in robotics and AI. We just got the news. This name changed a little bit in the new one. We just got the news that both of them were extended for 4 more years. And this is money coming from the government. Then we have already in place an interdisciplinary center that is the Health Science Center, where different members of the different institutes might participate. So usually, for example, for me, it's a 50 and 50 participation. So I'm 50% here and 50% there. But who has got rights to vote here are only the ones that have 100% participation in this center. So I got the right to vote only here for elections, political party. We have got another interdisciplinary center that is the interdisciplinary center. Let me see if I remember well the name on energy efficiency that has been recently approved by the Board of Governors. Actually, I am in the Board of Governors, so I am the representative of the Associated Press. But I didn't approve. At that time, I was not. I'm just recently from January, I'm here. So we actually are here. So I belong to the TeCIP Institute, that is Telecommunications, Computer Engineering, and Photonics. This building, maybe Stefano might be familiar with the architecture, is a typical architecture of the CNR. Indeed, we are in the area where the National Research Council is in Pisa. So it's just an additional building in a bigger area that is this one here. That actually is the biggest campus of the CNR in Italy, except the one in Rome, but Rome has got many administrative. So what do? We are two labs. One is related to embedded systems. So Retis lab is led by Professor Luca, and they do scheduling, cyber physical system, a big part on AI or trustworthy AI and all these important topics. And we do actually networks, but as you can see, we do from network and services down to the integrated photonics. So we cover basically the whole ISO OSI stack. So this is basically who we are. This is just a picture of what we do. So we do many things, from the routers and servers, data centers. You might recognize here some USRPs or some testbeds on the wireless communication, some robots for remote control, and this is the telepresence. So we have a cave, and we have also photonic radar, and actually this is a photonic integrated circuit. So we do many things, we are about, in numbers, between 60 and 70 people in the TeCIP Institute. So it's not small. And now with the government funding, it is going to increase a lot.
You say people, you mean faculty or faculty?
No, is let's say down to the PhD students. So from the faculty to the PhD students.
And you have postdocs as well?
We have postdocs, yes. Now, basically, with the senior check, we don't have any longer a senior check, so now they are called the researcher, short-term researchers. Yeah, but we do have postdocs, yes. So if you want to visit Pisa for a period, you are more than welcome. And so I close here with the let's say presentation of who we are, and I move quickly to the 6G. So, well, I'm always quite reluctant to tell about the generation, because you know that now the mobile communication generation is more a fluid evolution between the different generations. So we can say that this is 6G, but it can be the next generation of mobile communication. And these these figures are taken from a presentation by Ericsson, so in this white paper in February 2022. And basically the challenges that they highlight are trustworthiness, so trusted communication and computing for industry and society relying on critical information, sustainability, simplified life, and application demands. And so they envisions an evolution of the mobile communication from the well-known three use case scenarios of enhanced mobile broadband, ultra reliable latency communication, and massive machine time communication to a type of hexagon where we have immersive communications, global broadband, omnipresent IoT, spatio-temporal services, critical services, and compute AI services. So, and you can see that already in this slide, we see what the title of my presentation was. So communications and computing are really a single entity. Just to open a parenthesis, in Italy, we have these very strict and isolated sectors of to which we belong. So, for example, I belong to a sector that is called telecommunications. Somebody else belongs to a sector that is called signal elaboration. Somebody else that belongs to informatics. But now these different sectors don't have any more too much sense, in a sense that everything goes together. And so, in that white paper, they highlight 6G paradigm shifts. So we go from secure communication to trustworthy platform. So there is a lot of AI involved, but how trustworthy can be AI? So there is a big field of feature of trustworthy AI. From energy efficiency to sustainable transformation. From manually controlled to learning networks, and this is what we are working on mainly. From these physical and digital worlds to a cyber-physical continuum, we can hear a lot of digital twin of the network, digital twin of the application. From data management to data ownership, from terrestrial to global 3D connectivity. So we're involved also satellites, low Earth orbit, and all this part. From predefined services to flexible user centricity, and from data links to services beyond communication. So this is what they envision. And they have this list of 6G technology elements. I highlighted the ones that I will speak about. So you can read them by yourself, but I will focus mainly on the changes that are now ongoing between the split of the function from the RAN, so from the radio access network, and the core network. So they envision no longer a very strict differentiation by functions in the radio access network and the core network. And then I will speak about the data-driven architecture. Actually, Alessandro will speak even more about it. And then there is the part related to the network compute fabric, where 6G will offering computing intertwined with communication in a network compute fabric for high efficiency and dependability. What they call edge cloud continuum. So the data are processed no longer in the cloud in a central location, but they are processed while they are passing by from the edge to the cloud. And then trustworthy systems. So I will touch a little bit upon the confidential part of the computing and how we interpret it. Then let's start from the confidentiality preserving analytics for failure detection. So as you know, or you might know, there is this document by Etsy that defines the architecture of the zero-touch network and service management. What is zero-touch network and service management is, as we maybe learn during our studies, is closed-loop control. Nothing different from that. Like in automatic system, closed-loop control exists forever. So you have you measure the error between the target value and the reach value, and then you correct the errors and you try to reach the target value. Etsy tries to employ this, to exploit also this paradigm into the management of networks. So having a kind of, this is an example of loop. So this is called the OODA loop. So the observe, orient, design, and act loop, where this is the managed resource. You get data from the observation, you collect the data, you get the information to the analytics blocks that try to interpret a little bit the data. The analytic blocks gives insights to the intelligence that must take a decision. And then the decision is orchestrated and act upon the managed resources. So you clearly see here this closed loop. Alessandro will speak about the data collection. I will speak a little bit more about the analytics, and I think Alessandro also will speak about the orchestration and control. So what we are missing currently in our group is the intelligence part. So who does the
That doesn't sound
optimization? Sorry?
That doesn't sound.
It doesn't sound good, yes.
Yeah, okay, but we're not intelligent.
Well, it depends. We can be intelligent if it is just a threshold. So an if in the program, if this is greater than this threshold, we do this. No, but in a sense that we have some expertise, but we would like to have somebody working full time in this part. And this concept was also, let's say, considered, you might know, in the ORAN Alliance. So in the one of the implementation of the Open RAN concept. So you have, if you remember, the near real-time RAN intelligent controller and the non-real-time RAN intelligent controller, and they can implement different closed loops with different loop time. So in the milliseconds level or in the seconds, let's say, level. So fix this. You know that also in the RAN we have RUp and XUp that are applications that might implement some intelligence or analytics. So some blocks of this loop. So mainly the analytics part and the intelligence part. But actually, the XUp can be run by third parties. So it's not the provider that is asked to implement everything in RAN. You can ask a third party to implement an XUp that, for example, performs forecasting. So you have the current data, you want to forecast which will be the future behavior of the traffic. So, but sometimes, and these are the motivations of our work, the network providers don't want to share the data related to the networks with third parties because they are precious data they don't want to disclose. So we focus on this point. And the question was, could we send the data to a third party, anonymizing them somehow, but having the third party to run, for example, the AI algorithm on anonymized data and to give us the same answer that they would give us with, let's say, clear data. So data that are sent as they are. So in this way, the communication provider could get an answer from the XUp without disclosing actually their information. So, and we took the idea from the imaging processing world, because they had this question some years ago. So the question they had was, could we send a scrambled image to an AI engine? But can the AI engine classify the image even if the image is sent in a scrambled fashion? And they said, yes, in some cases we can do it. So we took this idea and we said, why don't we organize, and we applied it to the optical network, why don't we organize the data coming from an optical network? So, for example, the amplifier power, the bit error rate and so on. We scramble them. So we organize it in a matrix that has in the columns the different features and in the rows the time series. And we scramble it and we send it to the third party that analyzes them and gives us an answer saying there is a failure, there is no failure. So to picture the idea, it's like we have a matrix like that and we send it as it would look as a pointer to the x-axis. So it is a challenging question, and we try to implement it in this way. We collaborated in this case with a Brazilian researcher that actually was a research fellow in our department, but working remotely, and now is in the Los Alamos labs in New Mexico. And so we use the PCA, principal component analysis, to do this. So I leave you the slides so you can look at the papers also more carefully. I try to go fast on this. But I try to tell you the idea. Which is the idea? The idea is the following. We train the AI algorithm with data coming only from normal behavior of the network. And what it means training? Training means finding the principal components, and then in principal component analysis, just to give you a very short overview, principal component analysis is a technique that extracts from a set of data the principal component. So basically, it extracts the most important eigenvectors out of a set of eigenvectors. So the one that weights more. For example, if you have data in a 2D, if you have data only on the x-axis, your principal component will be only the x-axis. So no data on the y-axis will be important for you. So it will weight more. So in this way, you provide, and it is used actually principal component analysis for image compression. So that is a field where principal component analysis is used. So we do this, we train the machine learning network, and with training I mean we find, the eigen vector that give us a certain threshold only with the normal working condition of the network. Why we do that? Because it's much more easy to find data about the normal working condition, because as you know, a failure happens rarely in the network. So it's 99% of the time, and even more, the network is working. So with this trained network, we are able to have an error in reconstruction of the original matrix, so the error between the original matrix and new matrix, of a certain value. For example, 99% we are able to reconstruct the original data. So the error we consider is the Euclidean distance for the moment. Then what do we do? This is for the training. For the testing, so for the inference, we do the same thing with the new data coming from the working condition and also failure condition of the network. But because we keep anyway the principal components we selected for the normal working condition. What happens then? If the network is in working condition, the threshold of the error will be, the error will be at the threshold or below the threshold. But because the principal components are able to reconstruct the data with this error. But if there is a failure, the principal component will not be the same that we use for training, because maybe there are data that are in another direction of the principal component. So there, the error will be much higher than the threshold. And so for us, that is an outlier. And for us, that is a failure condition. So that is I don't want to go into details, so we can send you papers about it. So this is what we do. But how we preserve confidentiality? We preserve confidentiality by scrambling the data we sent to this engine. And we saw, and it is possible to prove that principal component analysis is insensitive to the scrambling, because the scrambling is basically a rotation of the axis. Well, we can see it well in 2D or 3D, but we cannot see it well in XD. So, because the principal components are insensitive to this rotation, so it works well. So, what we got is the.
Can I ask something?
Yeah, please.
So, is this to preserve the privacy of exactly that? What is being preserved here is the information about which component of the network is being affected by a failure, or the operator or the infrastructure owner that owns multiple of those?
It is actually the network itself. So which are the components that are in the network? So whether you have an amplifier or you have like a link is composed of amplifier, receiver, etc., etc. So if you send it as is, the third party could reconstruct your network. And sometimes it's not very well received by the network provider because they don't want to disclose how they set up their network.
But how is the operator then using the information that it's a failure if it doesn't know where?
The operator receives back the decision and he can descramble data, and then he can see exactly where the failure is.
Also, you're descrambling like the location of the component.
Yeah.
And then
So the operator
failure
scrambles
component-
them, sends it, receives back the answer, descramble them, and see here it is.
Luca, is this completely free? As you said, if you rotate, meaning that if you were not concerned about trustworthiness and being confidential, blah, 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 and you would provide to the third party the full, would you be faster? Would you be better? So what do you lose if you lose that?
Yeah, that's Stefan, actually a good question. We are still investigating this. In the investigation we did, there are many points here. The investigation we did was to send the whole matrix of observation of 10 hours to be processed. That is actually working, but for let's say real-time failure detection is not good. So in that case, we don't lose anything, but that is an optimistic scenario. So we are investigating whether if we, let's say, do this scrambling on a buffered, time buffered set of data, so every, 10 seconds, how much we lose. Because that would be very helpful for the fast failure detection, but we could lose something. So that is important. And that is also was a question that we received from a reviewer of a journal paper that we sent. So this was our answer. So it's a really work in progress. But it's a, very good question. So this is actually what we do. This is what we will present in OFC. Basically, what we had in this case was this network with two LiPads. The first analysis was done with a single LiPad. Here we have two LiPads, and we wanted to see whether the algorithm was capable of detecting the failure when it was affecting both of the LiPads. So we placed the failure in different locations. And just to be short, you can see here that here, let's say, where there is training this part, so where the network is in working condition, there are no outliers. That is here. But here is where the network has got failures. And you can see here, because we generated failures after the first amplifier, you see that here there are no outliers, while here both of the LiPads get affected by the failure. So, and these
Are these experiments based on a testbed or a...
Yes, these are based on this testbed that we have in our lab. What we emulated are the failures. So the failures are, emulated with this variable optical attenuator. So Alessandro did it, so he knows better than me. But basically, is a periodic failure generation. Yes, but these are based on the testbed. So, well, these are basically the conclusion. There is a lot of work to do, and especially what we discussed earlier, optimal matrix size. So, can we have a fast failure detection and an optimal failure detection, and also different algorithms, because we tried it with the PCA, but what if you use another algorithm? That is also important. Then smart NIC and network function acceleration. I try to speed up. I just found this paper by Samsung in the Samsung Research Communication in December 2022, and they have this let's say evolution of the function in the distributed unit, so in the RAN and in the UPF with evolved EU and what they call merge user plane. So I don't know, I cannot tell you too much about it because I still need to process it, but it seems that the trend, as I told you, is not to have any longer the real differentiation between RAN functions and core network functions, but having a mix of them. And where it is useful to put them some here. So you see a RAN related service function here, but also somewhere here, core network, common service function here and there, but I still need to process. But it seems that the trend of the researchers is going to a different balance between core and RAN functions. What do? We worked on the old paradigm when we have RU, so remote unit, distributed unit, and central unit. And we try to accelerate the functions in an FPGA, so a field programmable gate array. And the function actually we accelerated was the IFFT and the FFT, because it was the most suitable function to be implemented into an FPGA, because it's basically matrix manipulation. So, to be short, which was the main issue we faced? So, we inserted in a server where we had both low-fi function and also upper layer function. Some of them were implemented in hardware, some of them were implemented in software. But which was the main issue? The main issue was the following, and I think also is an important issue from the research viewpoint, how data that are in a server where there is acceleration and also normal CPU, how data are transferred from the CPU to the acceleration element. Because this might take a lot of time. In fact, if you have, for example, this is the input interface, and then you need to send the data to be accelerated down to the FPGA, they must go through the PCI Express interface. And that is the worst bottleneck, because you need to take the data, move it to the memory, then from the memory taken and sent to accelerate. So our approach is an approach that is followed also by many companies, is to do a smart NIC type of acceleration. So where data are sent out, so we looked at the downlink part, sorry, way too fast, are sent to the output interface without going through the CPU. So we did not go through this other communication, because these are huge bottlenecks. So this is the concept that you might know of the smart NIC. So having the elaboration done in the network interface card. So we implemented this with a high-level programming language for accelerator that is called OpenCL. And we implemented this in this small testbed. That is the one you have seen in some pictures, where we had servers that were equipped with both FPGAs and GPUs. So, and what we got, so this is the testbed. We compared the let's say the processing time of FPGAs and CPUs and GPUs. So you can see it here that what happens to the FPGA is that more or less with the increasing size of the IFFT, it stays more or less flat in terms of processing time. Why? Because it can exploit the parallelism of the FPGA. What happens to the single CPU? So one CPU core, you see that at a certain point, a single CPU core cannot keep up with the FPGA. So if you use a single core, using FPGA is much more efficient. Obviously, what happens if you use more cores, the performance are better. But you lose the cores for other applications. So imagine a scenario where you have to assign different computational resources to different tasks. In this case, it's much better to assign FFT or IFFT to the FPGA. There is also the comparison with the GPU, because you know that the GPU now are hype. But if you do not implement well the IFFT, even the GPU the GPUs do not perform very well, because you see that with the size of the IFFT, the GPU goes up. With a better implementation, actually the GPU can perform much better than the FPGA that is here. We did also a comparison on the energy consumption, and you see that the FPGA is very good in energy consumption per element. The GPUs are more performing, but they consume more energy. Then the last analysis we computed is, but how is impacted the processing time by kernel read and write? You see that the orange part is the kernel, so the amount of time taken by the FPGA to process the data, but you see how much is taken from writing and reading the data from the memory. So to bring the data from the memory to the FPGA, and that is a huge bottleneck. So that is what we are facing. So we are good in elaborating FPGA, but it is difficult to move data, and that is also a hype in some conference like hot interconnects. I close here in 5 minutes. There is in release 17 of the 3GPP, there was a working group trying to find out which are the key requirements of medical applications for 5G. And they classify the scenarios in static, fixed environment with a stable connectivity, moving, dynamically changing context with unstable connectivity, local inside the hospital facility, and remote far from the hospital. With this scenario, they combine the different scenarios and they had different applications. For example, augmented reality assisted surgery. What it is this is something like very futuristic, where the surgeon is helped by live reference medical imaging over wireless connectivity. Imagine an operation room with some medical images, for example, of the brain or some parts of your body, and they have it in real time. So they do some analysis in real time. The problem is that in the loop for receiving the image, elaborating it, and then getting back to the surgeon, they have to take into account the fact that the surgeon, when he cuts, he moves at a certain speed. And if the feedback comes much later, the surgeon goes on. So the cut is much larger than what he was supposed to do. So these are the constraints. So, and you can see, you can refer to our paper is in IEEE Access. So the surgeon often are comfortable with a latency that provides an accuracy of 0.5 centimeter at 30 centimeter per second and speed. So this is the 30 centimeter per second is the hand of the surgeon. So they say, if I miss of 0.5, fine. I don't want to miss more. So you need to give them the feedback in time. So the feedback is about 16 milliseconds to provide feedbacks to the surgeon. Otherwise, it goes too much on. So these are important requirements. Another requirement was the remote specialty practice. This is another type of application where you have a truck equipped with medical devices to do some medical examination in remote areas. And here the most important requirement is connectivity. What do? We have two projects. One is called 5G SOGE, sponsored by the region of Tuscany. And we do this kind of device for helping the first informal carer to help people that lay on the ground. So they have a sort of RFID tag. The information is sent to the hospital and sent to the emergency dispatch center, where they are listed with a set of options for assisting these patient. Imagine like the informal carer is somebody that doesn't know anything about medicine. It's like the automatic defibrillator that is around. And then the patient is sent to the hospital. We tried these, actually we applied to COVID by doing physical distance measurements. Then another point that we do is for the track, we do a connectivity analysis. It is possible to do the connectivity analysis by taking data from the AGCOM, that is the Italian National Authority for Communications, because the providers are forced to send to the AGCOM their connectivity speed. This project is done in the framework of a project that is sponsored by the Cassa di Risparmio di Lucca Foundation. It's for the inner areas of Garfagnano, of the province of Lucca. And this is the connectivity. So we do this, we implemented, actually Alessandro implemented this part related to the GIST, so geolocalization of the connectivity. You see ADSL, VDSL, EVDSL, and further to the home. We map this together with the location of some buildings or offices where a medical assistant can be provided. And this was the quality downstream, so from the center of the network to the remote areas. And this is, as you can see, much worse, the connectivity upstream. So this is used to decide where to deploy certain services. For example, where the connectivity is bad, you cannot send X-ray because they will never get to the doctor. But you can send, for example, monitoring of the glycemic level or something like that. So just to conclude, and sorry about taking a little bit more time, networking and computing integration has got high potentials. The important remarks are coverage is a must, and end-to-end latency contribution are both in network but also in computing. So, for example, virtualization, many advantages, but then you have to move from the stack from down, up, and down again. So there are hidden latencies there. That's also why they move from virtual machines to containers. And then it is important, as we have seen, where and how data are stored and transferred. And then let me conclude with a question mark. In my opinion, technology is moving much faster than application needs. I mean, in particular in telemedicine, what we can do with 5G could be done with 4G or even with 3G, because the reading of a glycemic level can be sent through an SMS. So, is it good or bad? I don't have the answer, so I let it open. Thank you very much for the attention. These are all the projects that in which the activities are included, and they are mainly sponsored by European Union, European Commission, Italian government, region of Tuscany, and also private foundation has this proximity care. Thank you very much, and sorry.
Thank you, Luca. One question, if possible,
Yeah.
or
Yeah. Alessandro?
because if you have a question, you can ask them. Yeah, as they do. Alessandro, now you have this very difficult task to keep your talk relatively short.
Sure. But I had the introduction to Sant'Anna.
Next. Okay. Okay. Can you see the screen from the remote? I think they see, but they can see. Yeah. Okay. Okay, so good morning, everyone. My name is Alessandro Pacini. I am a PhD student at the Scuola Superiore Sant'Anna. And today I'm going to present this presentation entitled A Flexible and Modular Approach Towards Zero-Touch Networking. I will keep my mask. Okay, so
And now the pointer, no. The if you took it out from the USB, is what? If you plug in the
okay, present it for me. So first of all, okay, so something about me. I have a bachelor degree in computer science, and then I moved to Pisa for my master degree in computer science and networking. And now, as I was saying, I'm in my second year PhD at the Scuola Superiore Sant'Anna. And what is my research about? Well, as you can see, my research proposal has the same name of this presentation. So today I'm going to present actually my research, and I hope that you are going to. So what is zero-touch networking? Okay, starting from our traditional network, as you know, traditional networks requires heavy configurations that are mainly regarding distributed intelligence, in the sense that networks have to be configured, requires heavy workload from the configuration point of view, and required a lot of convergence time and many other issues. And for this reason, we decided to abstract our networks. And so through the concept of network function virtualization and software-defined networking, we tried to detach the control plane from the data plane so that the intelligence of our network is actually moved and centralized. And with the network function virtualization, we can actually use generic hardware in order to do some networking computations. But what is zero-touch networking then? It's the actual next generation paradigm through which networks are actually able to self-manage. They are high-level policy driven, and they are able to self-configure, self-monitor, self-heal, and self-optimize without the human interaction. But the best part is that, of course, this allows you to make much more efficient proactive decision through the massive usage of AI and machine learning techniques. And as Luca was saying before, the zero-touch networking idea was one of the ones that proposed this idea was the European Telecommunication Standard Institute, formerly named Zero-Touch Networking and Service Management,
which is based on the closed loop automation, and so implementing the typical OODA decision-making steps, which are observe, orient, decide, and act. Those functions have been actually mapped over 4 functional blocks that are data collection for the observed part. So we have our managed resources that from which we get our data from, and we extrapolate some information from these managed resources that we send them over the analytics module. The analytics module implements the orient phase and produces some insights that are then forwarded to the intelligence module, which applies some decision that are finally forwarded to the orchestration and control module. So the orchestration, of course, applies the decision on top of the managed resources. Actually, ETSI produced and decided to add a 5th module that implements knowledge, and that actually is the data that we get from the network. And this 5th module basically is the knowledge level that all the modules produces data to and receives data from. So what are the problems then? Well, this type of architecture actually requires a deep redesign. So this means that the problem is that it's not actually fully defined. It will take years to get implemented since of the deep level of reconstruction of this type of network. And of course, the problem is that it's focused on access to network. So it did not produce the insights for different type of networks, such as optical or packets. So what we should do now? From our perspective, a very important aspect is that by taking into account that this next generation paradigm is going to arrive, we have to think about how we have to be prepared for this. And so we have to study each block features and requirements, and then what we should do is to extend our current generation of network so that we can embrace them when this new generation paradigm arrives, so that we can just plug our networks onto this closed loop automation. Indeed, the real meaning behind my research proposal title is actually the idea of facilitating the transition towards this next generation paradigm by extending current generation architecture with next generation tools. So today I'm going to present just a couple of research activities that we carried out in this context, starting from 2 modules that are the data collection and the data modules. And we will see how we produced a monitoring framework that implements both the data collection and the data module using Apache Kafka. And then we will see how we implemented for the orchestration and control module a system that allows to scale a software-defined networking architecture for clusters to a hierarchical paradigm. Okay, so let's start from the first one. So for the data collection and the data modules, what we have to think about, as we were saying before, on the requirements. So they have to guarantee, first of all, the scalability of the system. We have to think about not only what we need in this moment, but also on what we will need when new modules arrive, when new features will be produced and will be attached. Low latency communication, since those modules are actually impacting the closed loop interaction time, and of course continuous availability. The control loop cannot be stopped. And also flexibility. As we were saying, we have to think about those kind of modules as something that we have to be able to attach new modules to. And of course, all generation monitoring capabilities. So let me introduce you to Kafka. Apache Kafka is a distributed real-time and streaming platform, and it was originally developed by LinkedIn, and it is written in Java Scala. It is based on a publish-subscribe pattern, so we have multiple entities publishing data and multiple entities consuming that data. It offers a very low latency communication, high scalability, and it's strongly reliable. Let's see some Kafka concepts starting from the architecture. So as I was saying, we have those entities that are producing data that are called producers. And so producers are sending data towards what is the cluster. The cluster is composed by one or more entities called brokers. And the role of the broker is actually to receive the data from the producer, to temporarily store that data, and to send data to the consumers. And one of the brokers is then elected as the controller broker for the cluster. And then on the other side, as I was saying, we have the consumers, which instead reads the data from the cluster. And then there is the zookeeper ensemble, which has become also deprecated in the latest version of Apache Kafka, but was basically used to manage the consensus within the cluster. So what is a topic? A topic is a stream of related messages. So as I was saying before, producers and consumers produces data and reads data, and they did this through the abstraction of a topic. Indeed, multiple producers and multiple consumers can read and produce data onto a same topic, and this acts as a logical immutable log. And so this means that each consumer is independent from each other, and so each producer can decide to start reading from the beginning of the log, or from the end, or from a specific point. And this mechanism basically allows producers and consumers to be decoupled. Then there is the concept of partition, which is the actual implementation of a topic. So a topic is actually implemented by one or more partition, and it is practically an immutable log. Indeed, a producer is specifically producing data to a topic partition, and that's the reason why data that have to be ordered has to be sent over a same topic partition. And the best part is that this data sharding allows basically to scale horizontally onto the distributed architecture of Kafka, since partitions are distributed across groups. Another important concept is the one of the replicas. So basically, as you can see, each topic partition can be defined in two ways: as a leader partition or as a follower partition. The leader partition is the one that actually receives the data and sends the data to and from the producer and consumers, while the follower partition are the copies of the leader partition, and that are specifically distributed onto the other brokers. And their role is exactly the one of keeping in sync with the latest messages that have been produced on the leader partition. And this allows basically to say, okay, one of the leader partition has gone down for some reason due to a failure or any other problem. Okay, then there is another broker that takes its place, and so a new partition is elected as the leader one. Indeed, each replica can be in sync, and so completely aligned with the latest messages produced on each of the partition, or out of sync. An important aspect is the number of minimum in sync replicas that each partition can have. So this means that if I want that a new message has to be produced on a specific partition, then the min in sync replicas define the least number of in sync follower partition that has to be present in the system in order to produce the message. This practically means that a message with a minimum number of in-sync replicas defines that my message will be replicated for sure at least n times as the number of minimum in-sync replicas. And this, of course, represents the main reliability mechanism of Kafka. Final aspects, producers can be configured with the different type of acknowledgements, starting from the ACK type 0, which defines basically that my message has been received by the cluster just from a TCP perspective, so just an acknowledgement from the connection. ACK1, which instead represents that the cluster actually acknowledged me of receiving the message if just the leader partition has received that data, or a call, which means that all the follower and all the leader partition have acknowledged that message. And so this means that my data has been for sure replicated at least 10 times after the acknowledgement. On the other side, we have the consumers that instead can be grouped together in consumer groups. So this means that one or more consumers can consume in parallel the data produced on two different partitions. And this allows an horizontal scalability of the system, since we can deploy a variable number of consumers onto our system. And the best part is that this allows also a reliability mechanism at the consumer side, since if there is one more consumer within the consumer group with respect to the partitions, this means that if one of my consumers that is actually consuming data goes down for some reason, that will be another way for that. Yes.
How scalable is this Kafka thing?
It's actually it was used by LinkedIn in order to update all the feeds and messages within their platform. And the fact is that since it is highly configurable, you can define according to the bottleneck that you have in your system, you can scale both the producer at the system level, at the cluster level, or at the consumer side, according to your needs. So it's what makes it so powerful is exactly its configuration from the configuration point of view. So how scalable depends on what you are doing with your data, but Kafka, it allows a scalability at various levels.
So it could support telecommunication networks.
Yeah, sure.
With thousands
of
users.
We will see in very few slides how we actually apply this to net.
Maybe, I don't know, I'm not an expert, Sandro is much more expert than me. We can see it as a distributed database, that not a single database that got a single point of failure is less scalable in the sense that everybody must write.
It's software, of course. Where does it run?
You can install. I mean, it's fully supported on Linux. I don't know actually about Windows or Mac, but yeah. Okay, so the other building blocks that that we used for our architecture, other than Kafka, is Kafka Streams, which instead is a simple Java-based library, which implements both producer and consumer at the same time, but in the middle is able actually to apply both stateful and stateless commutations. Then there is Telegraph, which is a Go-based plugin-driven collector agent, which is very powerful from the point of view of connecting multiple sources to multiple destinations without changing your architecture. And it has a buffer for handling unsent metrics over the output. And of course, Kafka is one of the output plugins that it supports. Then there is InfluxDB, which is a very powerful time series database. And finally, Grafana, which instead is a platform for visualizing and querying the data from a database, time series databases such as InfluxDB. Okay, the final architecture is the one that is presented in this figure. So basically, we have. Let's see if I'm able. No. Sorry. Oh, yes. Okay, so in the upper part, as you can see, we have 3 brokers with 3 different instances running in 3 different machines. And we have 3 partitions that have been configured for each of the topics that are here present in the figure. And each of the topic has 3 replicas each distributed on each machine. And this actually allows to handle one entire broker machine instance. without losing any message, since the entire system has been configured with the strongest deliverability services. Then we have 4 topics. The first one, which is optical network, that basically receives data from a real optical network that you can see here at the bottom. So we have basically a Python script that reads data from a real optical network, and that's exactly the same network that Luca presented before. We have the Telegraph plugin that receives data from this Python script and sends all the metrics over the specific Kafka topic called optical network. Then we have the Kafka metrics topic, which instead we used to actually monitor the system itself. So we measured the CPU usage, the memory usage for each of the brokers, so that we can actually scale the system according to the specific needs of our architecture. Then we have the management part. And as I was saying before, the important aspect of our research is to take into account what comes next. So according to the closed loop automation, to the closed loop scenario that we have seen from the zero-touch networking scenario, we actually took into account that this could be a part of the zero-touch networking scenario. So we have an orchestrator that basically sends data to a management topic. What is sends? Basically, every time that a new light path is established on our network, the orchestrator sends a message on this management topic saying, okay, a new light path has been established, and these are all the devices that have been involved in this new light path. So what happens is that this management topic is then consumed by this Kafka Streams application. The Kafka Streams application have been used actually to read all the data from the optical network, but after a new light path is established, they start filtering the metrics according to the devices involved in the new light path. And what they do, they send the filtered metrics onto a dedicated topic. So we are going to dynamically generate through the light path X new topics according to the new light paths that have been established on the network. And finally, we have also on the other side the GUI output, where we have a Python script that reads the data from all the topics and writes all those data into an InfluxDB instance running on a different machine. And here we have 3 different dashboards. The Kafka dashboard showing the metrics about the Kafka metrics topic. The optical network dashboard showing data from the optical network topic, and the light path X dashboard, which is dynamically generated using both the data coming from the light path to the dedicated light path topic and from the management topic. This is the architecture that we tested, in which we tested the scalability and the performance of our system. So as you can see, we have 2 producer servers and 1 consumer server. And the aim was exactly to verify the performance of our system while increasing the number of messages to be sent on this architecture. And as you can see from here, we run different types of tests while increasing the number of producers and the number of consumer groups that are actually consuming data from different topics. And from the easiest test that we carried out, as you can see, we have the test tree in which we run up to 4,000 messages per second with a throughput of the consumer side of almost 70 megabits per second. And those figure actually shows here a capture from the consumer side. So as you can see, it's almost 70 megabits per, sorry. I'm so sorry. It's not working. Okay. Okay, here, as you can see, we have the throughput with a Wireshark capture of 70 megabits per second at the consumer side. But the most important aspect is actually that this other figure shows the impact of the test tree on one of the brokers involved in our architecture. And as you can see, while stopping and restarting the test tree scenario, we have just an average usage of the process from the Kafka broker, which is at 50% usage in the CPU, and even from the memory usage at the Java virtual machine, it's almost nothing. So we can scale much more this system. We can increase the load on the system, but we didn't have enough machines in order to test it even more. For what concerns some end-to-end latency tests, we use the test tree scenario as a basic load for our system, and we wrote a Python script to measure the end-to-end latency while increasing while sending messages over the management topic. So we have 3 producers, 3 consumers that are sending 10 messages per second for 10 times within the management topic. And those figures shows the end-to-end latency for each of the 3 conditions involved in this measurement. And we have an average latency of almost 50 milliseconds. But as I was saying, you have to think about that we can stop any broker in every moment, and we are not losing any message within this architecture. And we also carried out other tests showing how the failure of a broker actually affects the latency of the average latency of the messages sent while stopping a broker, and it was approximately of 1 second. Okay, so what we have seen that we developed an architecture for persistent optical network monitoring, but that can be also applied to many other scenarios. That it's scalable, reliable, and low latency. We have seen that we actually thought about this architecture with the flexibility and the dynamic monitoring in mind by the usage of Kafka metrics and so monitoring the architecture itself while processing the data itself and through the live path topics. And of course, we can add to the system as many other modules as we want, since it is a pluggable architecture. So we have seen the part related to Apache Kafka. Let's see very briefly the one related to the SDN cluster. So as I was saying, we focused on the orchestration and control part. And the orchestration and control module must guarantee, first of all, high-level decision and policy controls, abstraction over managed resources, and of course, reliability and scalability. But as for before, we have to ensure a flexibility to the system while preserving all generation critical capabilities. So let me introduce you some typical SDN architectures for small medium networks. And for those of you that doesn't know, ONOS is one of the most famous software-defined networking controllers. It is open source, was originally developed by the Open Networking Foundation, that now it's under the Intel company. And ONOS basically can be implemented as a single instance. So we can have a single instance of a controller managing the entire SDN domain. Of course, this is the easiest configuration, but it suffers from single point of failure. So for this reason, there is the cluster configuration in which one or more SDN controllers act together in order to manage a same network topology. And so if some of the one of the ONOS controller goes down for some reason, then there is another one that is able to take the control. And so for this reason, we have an increased resilience and scalability on the system. But the problem is that we have strict synchronization requirements among the ONOS instances belonging to that cluster. Indeed, the problem is that both of them are not actually suitable for large-scale networks. For this reason, when we move to much larger scenario, the key idea is actually to divide the network into multiple SDN domains. And so the fact is that we have one or more honest instances managing a subset of devices, and so we have smaller SDN domains. But the problem with those kind of scenarios is that we want actually to keep the typical centralized management capability of the SDN scenario in this context. And so for this reason, we have two types of configuration. The flat one, in which basically we have the honest instances managing the subset of devices that shares their own view with all the other honest instances. And so we have that all of them are actually involved in a same common view. We have the same number of resources as it was used as a cluster, so it's pretty efficient, but it's not efficient with few controllers, since this kind of architecture typically involves publish-subscribe communication. So the other approach is the hierarchical one. In the hierarchical approach, we have the honest instances that manages the subset of devices. That manages the subset of devices. Okay, here we are. Okay. No, okay. That manages the subset of devices that instead of sharing all their topology view with all the other honest instances, they share it with this new honest instance type, that is the parent. Indeed, the centralized view is only at the parent site. We have a workload that could be balanced among the parent and the children, but in this case, it is not efficient if we have many controllers, since this approach typically involves point-to-point communications. And the best part is that both of those approaches can be actually combined with the cluster configuration. So we can increase the resiliency of those type of configuration within the cluster one. So let's move to our solution, which is a specific architecture for enabling honest cluster to a hierarchical design. And so basically our aim was to keep in sync the child topology views at the parent cluster, even if some failure occurs both at the child or at the parent. And in order to do that, we developed two types of application: the hierarchical sync child running on top of the child clusters, and the hierarchical sync parent running on top of the parent cluster. And the key aspect is that both the child application and the parent application have been specifically developed to take advantage of the distributed environment. And so they actually populate the view at the parent site by propagating the events that are generated from the child topologies up to the parent one. And the fact is that those events are actually carried out using low latency gRPC channels. So in this figure, as you can see, we have a much more detailed scenario in which we have the honest instances for each of the honest clusters. We have our application running on top of each applications, and so communicating among the child and the parents. And then what happens is that we have an event that occurs on one of the child topologies. Then we have the honest cluster that processes and dispatches the event within the cluster. And then we have our application. Our application, as I was saying before, has been developed for the distributed scenario. This means that applications that are running on top of a cluster is actually replicated on top of each honest instance within that cluster. And so this means that all the components that builds up our application are replicated on top of each honest instance. And so if there is at least one honest instance running within each cluster, our synchronization mechanism goes on, and so the system keeps moving. So, as I was saying, we have the very first component of our application, which is the listener. The listener captures the event, converts it into an intermediate format, and then sends it to a distributed queue within the TONS cluster. And that's mainly done for distributed resiliency purposes. Then there is the sender component, which instead retrieves the event from the queue and sends the event using the locally running gRPC client. Then the event is sent to a child, from the child to the parent cluster using the gRPC channel. And then there is the hierarchical sync parent, which runs the receiver component, which receives the event from the gRPC server that it's running locally, and it stores it into a different intermediate queue. And then there is finally the publisher component, which instead retrieves the event from the queue, reconverts it into its original format, and then publishes the event into its local queue. So the final outcome is that child and parent topologies are completely aligned. So this is just a very short video of how the system actually behaves. So in the top left part, we have the child one running 2 on instances, and on the bottom left part, 2 on instances running onto the child 2. And on the right part, we have the parent. So what we are going to see is that through Mininet, we are going to generate two topologies attached, one to the child cluster 1 and one to the child cluster 2. And here at the parent, we are going to see both of them. Okay, so I'm running the command for the Mininet network. And then now the network starts. Yeah. So as you can see, on the left, we have the two child that are attached to the real devices, while on the right side, we have the parent that just receives the update. And the fact is that, as you can see, the two networks have been attached using an intermediate link, and that is actually that has been created using a virtual Ethernet interface. And the main reason to do that is because we actually used this an additional view at the parent side, showing the clusters showing basically the topologies for each of the clusters. And if there are some links in the middle, then there should be highlighted, like as you can see here. So the future step for this work, since it is a very strong and solid starting point for controlling multiple types of software-defined networking domain, our future steps will be basically to abstract the managed resources that are under. And what we are going to see is how we are going to extend this to also manage a software-defined radio access network scenario. And of course, to apply some decision from the top. So we will try to use the parent in order to forward the decisions to the child, to one or more child. And finally, we will plan to make some high-level intent that can move from radio access part up to the core network. So we have seen both of them. So some conclusions. Basically in this presentation, we have seen how the zero-touch networking will completely change the concept of networking, but mainly why research is crucial for adapting our networks to what comes next. And that was it. Thank you. If you have any questions, yeah.
I have a question.
Yeah.
So you are using Kafka to get all the different closed information, and you're also using bonus as a single, every kind of cluster that you're making.
Yeah.
So how do you combine both two things? So how is every single element of the cluster, which should be the same because it's just a replica, get information, and how to centralize that in the upper level that you were mentioning?
Okay, so my plan is not actually to put everything together because let me explain this too. So as I was saying in the initial part, I think that our work should be crucial in order to think about on what there could be behind the zero-touch networking paradigm. Since there are no actual implementation, there is just a couple of white papers on top of that. We don't have a very defined idea behind what there is. So we have to think and rearrange our architecture based on some concepts and requirements on top of each module. So, in my opinion, the work based on Kafka could be crucial for some specific monitoring capabilities, because it's not a typical approach to make monitoring data so reliable, so well acknowledged. Indeed, my idea was actually to point out that, okay, some information could be sent using strongly acknowledged delivery, and some other not. And here, I think that Kafka and Honos could be like the complementary part of each other. So we can see Kafka as the monitoring part, while the gRPC-based synchronization as the control part. Because I think that publish-subscribe communication are optimal for massive data usage, while if you have to think about control operation, you cannot pass through publish-subscribe frameworks, because otherwise you are going to waste so much time that could be crucial for the control loop scenario. I don't know if your answer, if I
Yeah,
answer.
so starting with the first drawing that was Professor showed, the four edges. So you're saying that you use, let me get it correct, Kafka on the one on the top left, you want to get data, and these data are interpreted in some ways in the other edge, and then everything is taken in the lower edge. So we are not getting all the data, but you're getting just the one that are important for the specific.
Exactly. I mean, the knowledge part, the one in the middle, you can see it as whatever I need, I'm going to ask it.
Okay.
It's really flexible. There is no strict architecture on top of that.
And if I may add something, the knowledge part in the middle is not only knowledge about the network, but it is also knowledge about how the other different blocks perform in the past. So it is also monitoring how the different blocks behave. So it is a monitoring of the blocks, not only a monitoring of the network. So for example, I don't know, if you say, if you are using reinforcement learning, that data is storing, those data are storing the past experience by the reinforcement learning. So did I do good? Did I do bad? So
I mean, for the Kafka architecture, as I said in the presentation, the topic related to the performance of the cluster itself actually means that the control loop does not have to be just focused, as Luca was saying, on the managed resources, but also on the architecture itself. Because if for some reason I need more traffic to be handled, but my architecture is not scaling as well, I have to predict that in order to make things working. So I need another broker. I have to know that, and I can think about that by just looking at the performance of the cluster itself.
questions from remote?
Yeah. Do you have any questions from remote?
I have, but I'll ask in person.
Yeah, there was someone.
What?
No, there was someone asking a question
Hmm.
online again. Was someone asking a question online?
No, I just mentioned that I will ask in person.
Okay, perfect. Thank you. So, I don't know, Stefano left, but I think
Yeah.
you can.
All right. Thanks again for the talk.
Thank you so much for the invitation.
Thanks to everyone online for joining. So.